Hi. In the first lecture, we discussed what complexity was, its attributes, and why it was important. And then in the second lecture, we introduced the concepts of Mount Fuji landscapes, rugged landscapes, and dancing landscapes. And we made a key distinction between difficult problems, which is finding a peak on a rugged landscape, and surviving in complex systems. These are situations in which the landscape dances, and we need to adapt and learn in order to survive and be successful. Now, in the second lecture, we observed that interactions between the multidimensional choices of the same entity produce a rugged landscape, and that its interdependencies between the actions of different entities, different people, different firms, combine with adaptations that are going to make the landscape dance, that create complexity. Implicit in that characterization of interdependence was the idea that the entities were connected in some way. And it was also the case that in our many examples, the entities were, for the most part, diverse. So what are we going to do in this lecture? In this lecture, we're going to dig more deeply into the four main attributes of a complex system: interdependence, connectedness, diversity, and adaptation and learning. And we're going to see how those things generate complexity. What we're going to do is we're going to get dialed into complexity, and I mean that in a literal sense. So I want you to imagine yourself sitting in front of a box. On that box are four dials or knobs, and above one of the dials it says diversity, and above another it says connectedness, and another it says interdependence, and above another it says adaptation or learning. Each of these dials can be set from some number between 0 and 10. So if we set the diversity knob at 0, that means every entity is the same, every agent's the same. If we crank it up to 10, they're all different. Same goes for connectedness. If we set it to 0, nobody's connected to anybody. If we set it to 10, everybody's connected to everybody else. And the same holds for interdependence and adaptation. Each of those knobs we can set at 0, or we can set them all the way up to 10. So for example, if adaptation is equal to 0, that means no one's changing their behavior. The landscapes are fixed. And if it's at 10, everybody's instantaneously jumping to a peak. That's why I said we're going to get dialed into complexity, because we're going to spend this lecture twisting those dials to see what combinations lead to complexity and what don't. Now, what's really fun about these experiments is they're not passive observational lab experiments. We're not going to put on like white lab coats and sit back and watch what happens and record it in our logbook. The chemical reaction appears to be emitting a toxic odor. These are going to be active thought experiments. So when we twist the dials, that's just the beginning. Once we set the values, we've got to sit back and think through what's going to happen. Now, as we turn the dials, we're going to find that contrary to what we might have expected, we're not going to get complexity at the extremes. We're going to find that complexity exists in a region that I like to call the interesting in-between. What do I mean by that? I mean that if things are too connected, if everything connects to everything else, we tend not to get complexity. Instead, we're going to get statistical regularity. On the other hand, if connections are rare, then a system just doesn't have enough going on to produce complexity. Therefore, for complexity to emerge, it must happen in this interesting in-between space, the space between boredom of no connections and the unproductive mangle of too many connections. We're going to see how this insight of complexity lying in the in-between region plays out for all four attributes, all four dials. But before we can do that, we need to come to a common understanding of what sort of behaviors a system might take so we can identify situations that are complex from situations that are not. So we're going to use a classification that Stephen Wolfram, a physicist, created. Before we start, though, I've got to be very careful in explaining what it is we're going to be categorizing. We're going to be categorizing both the system itself, the rules it follows, and the initial states. What do I mean by that? Well, let's take a family. A family consists of interdependent, diverse actors. It's true of my family anyway. If we set that family down at the dinner table, well, we might find that they settle into a nice, stable pattern of behavior. So we might say the family's stable. However, let's take the same family, put them in a car for 36 hours. In this case, their behavior is going to be, well, let's just say complex. We might have long periods of silence, followed by violent eruptions. So we can't say that the family is stable, and we can't say the family is complex. It can be either one. Which one it is depends on the state the family starts out in, whether it starts out at the dinner table or whether it starts out in the car. The same is going to be true of any complex system. Its behavior can depend both on its initial state and the rules followed by its parts. So that's how we're going to think of systems. Now, once we think of systems this way, Wolfram breaks them into four classes. Class 1's behaviors are stable. These are what we call single-point equilibria. So remember the case of our ball sitting at the bottom of a basin. That's a stable equilibrium. If we push the ball up a side, it comes back. Now, you might say a ball in a bowl isn't very complex, and that's not, right? But it's also true that we can have systems of diverse interacting agents that end up looking like the ball in the bowl. So this would be true of a market. If you go to a farmer's market, we might see a fairly stable set of prices and sales. So the market's in equilibrium, even though it's got diverse interacting agents. The second class of behaviors are periodic orbits. A periodic orbit is a regular sequence of states. So a stoplight cycling through red, yellow, green is a periodic orbit. The Earth rotating around around the sun is also a periodic orbit. Now, periodic orbits don't need to be physical. If I write down a mathematical model of predators and prey, I'm going to get cycles in which populations of rabbits and foxes oscillate in a regular pattern. The third class behaviors we're going to consider are chaotic. Now, by chaotic, I mean that they're extremely sensitive to initial conditions. If we take two initial states that differ just by a tiny bit, we're going to see that their resultant paths are going to diverge sufficiently that in a relatively short period of time, that we may not be able to tell the two apart. So metaphorically, this means that a butterfly might flap its wings and redirect a monsoon or a hurricane 6 months later. That's what we mean by chaos. Now, the final class of behaviors, class 4, what Wolfram calls class 4, are what we call complex behaviors. Now, like periodic orbits, complex behaviors have regular structure. But unlike simple periodic orbits, these patterns are longer, and they have what mathematicians call high information content. Roughly speaking, this means it would just take a long time, a lot of information to describe them. That's why life is complex. It's not easily explained. Stock markets are complex, and international relations, and families in the car. System behavior in these cases is not regular. No family, company, or country runs like clockwork. But they're not chaotic either. They lie in this interesting in-between. They have structure, but the structure isn't easy to define. Okay, so now I've got this really interesting question. What has to be true about a system in order for it to fall into one of these four classes? Or in other words, what makes a system stable and what makes a system chaotic or complex? Let's return to our box with the dials and do some experiments. Let's start with interdependency dials set at 0. So each person is completely independent of anyone else. She just does what she wants without any concern about what others do. What might be an example of this? Well, suppose you're thinking about what to wear. Do you put on a sweater? That decision has no impact on anyone else. So if we looked at sweater-wearing behavior, or the color of people's sweaters, we can just sort of count up what happens on average, and we're going to find that it's probably in equilibrium. The colder it is, the more people that wear sweaters. There's nothing complex. But suppose we ramp up the interdependencies. Let's think about junior high school students, and they're wearing sweaters. Well, now these students are thinking, I want to wear sweaters that look like my friends' sweaters, but I don't want to wear sweaters that look like the people I don't like sweaters. Once we get this, we've got interdependencies, and we've got the potential for complexity. And we end up with junior high school students standing in front of the mirror, right, perplexed about what to wear. That is complexity. It's caused by interdependence. Let's turn that dial even more. So now every student cares about what every other student wears, and every single item that the other students wear. Well, now we've drifted beyond complexity, and we've just got a mess. Because if one student changes his outfit, this could result in everybody else changing their outfits. So we're going to get something that's closer to chaos. We're going to have extreme sensitivity to initial conditions. One change in an outfit leads to just a mass set of changes. Now, it's not always going to be the case that too much interdependency leads to chaos. Sometimes we get, remember what I've called, an incomprehensible mangle. So if I let a 10-year-old loose in the kitchen and just let them start mixing up ingredients, they're going to throw in all sorts of things, but nothing interesting is going to emerge. It's just going to be pretty much a mess. So what we get, right, and this is the key point, no interdependency, it's not complex. Too much interdependency, it's either chaotic or a mangle. Complexity happens when interdependency is in the middle. Okay, recall that interdependency refers to whether other entities influence actions, while connectedness refers to how many people a person connects to. So first you can imagine someone disconnected from everyone else. To be disconnected, that means you've got no interdependencies. No one has any effect. So you just do what you do, and there's no complexity. So let's hold interdependencies at some sort of constant or moderate level and just change the connectedness. So what I mean is that I'm not going to change how much someone matters to you, but I am going to change how many people matter to you. So to put some structure on this, I'm going to consider two games. These are formal games that game theorists, people who study strategy, consider. The first one is called a pure coordination game. In the pure coordination game, the object is to take the same action as the people you're connected to. An example of a pure coordination game that we play every day is the greeting game. In the greeting game, when you meet someone, you've got to decide, are we going to shake hands? Are we going to kiss on the cheek? Are we going to hug? What you've got to do is you've got to pick a simple rule and you've got to follow it. And it's important that you do the same thing as your friends. Because if you go to shake hands and they go to hug, it's sort of awkward. Now, let's suppose we've got a network of people that are playing this game and they're trying to decide on a rule. Well, what we're going to do is we're going to assume that they best respond. We're going to use this rule throughout the lecture. By that I mean they're going to take the best response. They're going to do the best thing given what their friends did yesterday. So if yesterday your friends were mostly shaking hands, today you'll shake hands. If yesterday your friends were kissing, then you'll kiss. Now, if the system is hardly connected at all, say each person has like one friend, then the system is going to go to an equilibrium, and some pairs of friends will shake hands, some will kiss, and some will hug. Now, if we make the system a little bit more connected, partially connected, well, initially some people will shake, some people will kiss, some will hug. Some of the shakers may switch to kissing, some of the kissers may switch to hugging, and so forth. And after a while, perhaps after a long while, we can show that this system is going to settle down into equilibrium, but it's going to take a long time. And pretty much everyone will be doing the exact same thing. All right, now let's turn the dial even further. Let's suppose that everyone's connected to everyone else. Well, if everyone's connected to everyone else, people are going to very quickly converge on whatever action is most popular, kissing or shaking or hugging. And the result will be an equilibrium that arises almost instantaneously. So in this pure coordination game, what we get is if connections are low or if connections are high, boom, the system just goes to equilibrium. But if connections in this intermediate range, it could take a long, long time to get to that equilibrium. So we're going to get some complexity and then an equilibrium. Now I want to change the game. Now that we've got this idea about connections matter, I want to change the game. And I'm going to change the game to rock, paper, scissors. In rock, paper, scissors, remember scissors cut paper, paper covers rock, and rock smashes scissors. Rock, paper, scissors differs from pure coordination in that now I don't want to match the people I'm connected to, I want to mismatch them. I want to do something different than they're doing. So let's suppose that we're very loosely connected. So I've just got one friend. And suppose that the person I'm playing is playing paper, then I want to play rock. Now, let's assume that we best respond. This means that the person who's playing paper, which beat rock, so if paper beats rock, they're going to stick with it, right? Because it's the best thing to do against rock. But the person who's playing rock is going to say, well, wait a minute, my opponent's playing paper, so I'm going to switch to scissors. That's what we call a best response, because the rock will smash the scissors. Now, in the next round, the scissors person is going to stand pat because he won, right? The scissors cut the paper, and the paper person is going to switch to rock. Now, if we keep going with this logic, we're going to get a cycle, and that cycle is going to be of length 6. The first player is going to play paper, paper, rock, rock, scissors, scissors. And he'll do that again and again and again. The second player will play rock, scissors, scissors, paper, paper, rock. Each of them is going to win half the time, and we're going to have what we call a periodic orbit, what Wolfram called a class 2 behavior. Okay, let's turn the connectedness dial all the way up so that everyone plays everyone else. So now everyone in this whole population of players is playing every other person. So the first time these people play, let's suppose a majority of the people are playing rock. That means the next time everyone should choose paper, because paper is the best response. But then the next time everyone should choose scissors, because scissors is the best response to paper. Well, then after everybody chooses scissors, the next time everyone should choose rock. So here we have a simple 3 cycle. It just goes rock, paper, scissors, rock, paper, scissors. So what we see, not connected, we get a cycle. Fully connected, we get a cycle. What about in between? What if people are somewhat connected? Well, in this case, it gets complex. So to make it simple, let's put people on a checkerboard. I'll explain why in a second. And let's assume that each person plays its 8 neighbors. If you're on a checkerboard, there's 8 squares around you. Now, if you run this model with each square best responding, you're going to get very complex dynamics because everyone has slightly different neighbors who are playing slightly different strategies. You're not going to get simple cycles. You're going to get all sorts of interesting patterns that ebb and flow. You're going to see people sort of taking these weird patterns through rock, paper, and scissors. Now, I recognize that this seems very, very abstract. But the reason I did this example is because it's very real. In your guts at this very moment, each one of us has several types of E. coli. Some of these E. coli are sensitive, others are resistant, and others are toxic. Now, these E. coli are in effect playing a game inside our gut. And if we think of a head-to-head matchup, the sensitive E. coli are going to beat the resistant E. coli because the sensitive E. coli are simpler. They're simpler so they can reproduce faster. They've got shorter DNA. However, the sensitive E. coli get beaten by the toxic E. coli because they can destroy them. The toxic E. coli gets too toxic for the sensitive ones. However, the resistant E. coli, because of their longer DNA, they can defend against the toxic. So resistant defeats toxic. So in short, in your gut, in the lining of your gut, you've got a real-life game of rock, paper, scissors. But instead it's called sensitive, toxic, resistant. Now there's an article published in the journal Nature by Marcus Feldman, Benjamin Curran, Margaret Riley, and Brendan Bohannon. They did the following experiment. They took these 3 types of E. coli, they just scraped them out of someone's gut, and they put them on a slide, the kind you'd put under a microscope. So what this is this is an analog of our checkerboard experiment, right? Playing rock, paper, scissors, but it's real. It's with real E. coli. What did they find? They found complexity. What they found were these complex, diverse patterns of E. coli. To discern whether these patterns depended on connectedness, what they then did is they took these same E. coli and they put them in a beaker and they stirred them. Now by stirring these E. coli, that meant that every E. coli was connected to every other E. coli. So now we got full connectedness. Well, what happened then? Well, what happened is one of the E. coli run out. So the system wasn't complex at all. You get an equilibrium. So it's interesting, we see real-world science agreeing exactly what we saw from our simple thought experiment. If we had a moderate level of connectedness, what we got was an interesting phenomenon. We got complex outcomes. But if we had too much connectedness, with every E. coli connected to every other E. coli, we got an equilibrium. Here's where it gets even more interesting. If you take a game theory course, and my PhD was actually in game theory, you study the strategic behavior of different players. These can be firms, these can be political entities, these can be 2 people playing tennis. It shouldn't shock you to find out that most of the results we have in game theory consider either 2 players, which are low connectedness, or an infinite number of players playing one another, which is full connectedness. Because with 2 players, it's not too hard to figure out what to do. Right? You just figure out what the other player is going to do and you respond. And with an infinite number of players, you're just responding to this population, to statistical regularity. And so what again you get is predictability. So it's pretty easy to figure out what to do on average. So that's not very hard either. So what's interesting here is when you've got moderate levels of connection, each person is playing sort of a different game in a sense. Even though they're playing the same fundamental game, they're playing a different set of players and they confront a different situation, a different landscape, if you will. So the game becomes too complex to analyzing using mathematics. So as a result, game theory tends to spend its time ignoring the interesting in between and concentrating at the dial being turned to low connectedness or high connectedness. Okay, we're halfway home. Too little or too much interdependence, or too little or too much connectedness, and we don't get complexity. Complexity happens in the in-between. Let's go to diversity now. When we say diversity, we need to clarify what we mean. Diversity of what? If we're talking about an ecosystem, we might mean diversity of species. In an economy, we might mean diversity of firms or products. In a chemistry classroom, we might mean diversity of elements. What we don't mean is variation, which is slight differences in the members of a population. We're going to revisit this distinction in an upcoming lecture. Here, when I talk about diversity, I mean differences in types. Different types have different functionalities. So let's begin in the chemistry classroom to see how levels of diversity influence complexity. Let's use elements as our type. If I have no diversity, if I've just got a bunch of carbon atoms, not much interesting happens, right? But when I start to mix together a few elements, I might get some stable compounds. And if I mix sodium and chloride, I get salt. If I mix hydrogen and oxygen, I get water. The fact that salt and water differ in kind from their parts is emergence, right? This is something we talked about before and we'll talk about later. But for the moment, what I want you to recognize is that if we mix a few elements together, we get interesting things popping out, like when we mix baking soda with vinegar and get a volcano. So it should be pretty clear here, no diversity, not much happening. Increase the diversity so that entities with different functionalities interact, and we can get something complex. But what if we go crazy and just start mixing together a whole slew of elements, carbon, copper, hydrogen, lithium, beryllium, etc.? Well, we're likely to get gray goo, just a mess. So again, we see this same sequence of phenomena as we turn our dial. We go from simple to complex to a mess. But wait a second, you might say, what about ecosystems? Does this relationship hold? Let's take a low diversity ecosystem like the Sahara Desert. The Sahara is bounded on one side by the Atlantic and on the other side by the Red Sea. So roughly speaking, it covers the top half of Africa. It's about the same size as the continental United States. It's mostly sand dunes and buttes, but it's not barren of animal life. You can find antelopes, gazelles, hyenas. There's even some badgers and gerbils. Now, the best estimates are there's about 100 species of mammals and 100 species of each of birds and reptiles in the Central Sahara, and maybe 500 plant species. Now, Given that the Central Sahara gets between 5 and 25 millimeters of rain a year, that's not really bad, but it's probably not complex. By contrast, let's look at the Amazon. The Amazon River Basin is estimated to have over 5 million species of flora and fauna. One 25-hectare region of the Yosemite Forest in Ecuador, which has been studied, supports over 500 species of birds and 1,100 species of trees. 25 hectares is about 50 football fields. It's about the size of the Mall of America. To put that number of trees, 1,100, in perspective, the United States has approximately 850 species of trees. Due to deforestation, each week the Amazon is thought to lose nearly 1,000 species. That's more than the entire Sahara contains. That's in a week. So despite all this diversity, the Amazon rainforest is not gray goo. It's complex. So here it seems like we've turned the dial a long way. Does that contradict the idea that complexity happens in between? No. Here's why. The diverse Amazon ecosystem has been constructed over a long time, with each species adapting and evolving to fill in a particular niche. This is a process called niche assembly, and it requires a restricting of interactions with other species. If rather than construct an ecosystem, we just randomly toss together species and see what happens, we won't get complexity. We're more likely to see a collapse in the number of species. So what I'm saying here is, even though diversity is high, the system is responding by lowering interactions. Now, this isn't just intuition. Robert May constructed a theoretical model in which to explore how robustness of ecosystems correlated with diversity. So in this model, he created species that ate and were eaten by other species, and he just selected them at random, right? Who ate what? Who eats what? He found that as he increased diversity, beyond a certain point, robustness decreased. The complexity went away, and you ended up with systems that just collapsed. These systems were not likely to sustain complex dynamics. So how do we make sense of all this? Okay, so think back. May did something similar to what we did in our chemistry lab. He just randomly mixed up together. If we have random diverse types, then we get the result that too much diversity leads to either a mess or a collapse. However, in the Amazon rainforest, the species have had a long time to construct their behaviors and their niches so as to create a robust, complex whole. Therefore, it's possible for systems with increased diversity to be more complex. It's just not likely to happen by chance. So, if we think about cranking up the diversity dial, we should not expect that as we add diversity, we get more complexity. We should get the opposite. We should get a collapse and a decrease in complexity. This is why ecologists worry so much about invasive species, such as cats in the Galapagos and plants like purple loosestrife or garlic mustard here in the United States. These are increases in diversity that do not increase complexity. Instead, they destroy it. Okay, we're now ready to study the relationship, the last one, the last dial, between complexity and adaptation and learning. Now, if we think of turning this learning and adaptation dial, we don't want to just think of turning the rate at which these entities adapt, because then all that would do is make the system go faster, and there's really not much interesting to talk about. So instead, what we want to do is we want to think about turning this last dial as making the learning go faster, as making the parts smarter, making them more intelligent. So let's keep with our pattern. Let's start out with no learning, right? No adaptation. We've got simple parts that follow fixed rules. We'll see in a few lectures when we talk about something called the game of life that it's possible for simple fixed rules to create complex behaviors. However, it's not likely. So note that we encountered this same insight when we talked about diversity and complexity. With fixed rules in our chemistry lab and in May's computer model, when we mix too much stuff together, we don't get complexity. Now, a little learning or adaptation goes a long way. It allows the parts to figure out how to interact with one another and how to create a coherent, complex whole. At least it can. What happens, though, if we crank the learning dial all the way to the right? The answer is often we get equilibrium. Now, we can see this as follows. Suppose we didn't get an equilibrium. Suppose the system stayed in flux. Well, then it would be the case that some entity would want to change what it's doing. But if that's the case, the entity, if it's super smart, should have already changed what it was doing. So let's allow our entities to be people. If everyone's super intelligent and we're all optimizing relative to what everybody else is doing, then the system should be in equilibrium. Because if it wasn't in equilibrium, someone should have done something different, and since we're super smart, they already should have done it. Now, this isn't saying that everyone will best respond in the next period as in our game of rock, paper, scissors. This is saying that at every moment, everyone is optimizing. In game theory, this is known as a Nash equilibrium. This is a core assumption of neoclassical economics, that people optimize. If people can optimize, we don't get complexity. We get equilibria. This is why economists believe markets are in equilibria, because they think that people are smart enough to solve the problem, and if everybody can solve their problems, the system is going to equilibrate. Now, we'll see later on when we talk about negative feedbacks in a later lecture why this isn't necessarily a bad assumption for markets. However, it's not a good assumption in all cases. And for the moment, I just want to focus on this idea of why ratcheting up sophistication leads to equilibrium. Indulge me in a quick story. This is about the late Marion Tinsley and Jonathan Schaeffer. Schaeffer's a computer scientist. Tinsley was a mathematician, and he's considered the greatest checker player in history. He was world champion 20 times, and he's reputed in his entire life to have lost less than a dozen games. This is 45 years of playing checkers. This guy lost less than a dozen times. Tinsley spent something on the order of 10,000 hours in graduate school studying checkers. Okay, a good game of checkers is complex. Each person's adapting to the moves of the other players, and as a rule, the smarter the players, the more complex the game. By the way, the reason checkers support so much complexity is it's got lots of possible plays. There's 500 billion possible plays of the game of checkers, to be exact. So enter Jonathan Schaeffer. Schaeffer, with a group of co-authors, solved checkers. That's right. In 2007, they wrote a paper published in Science with the title, Checkers is Solved. What this means is that checkers is no longer complex. We can just look at their solution and follow the rules. That solution will be in equilibrium. That equilibrium, by the way, is a draw. It's just like tic-tac-toe.